So this session on wave theory of light, I am going to discuss the concept of diffraction of light. Diffraction of sound you might have heard if you had shown interest in sound. I mean interference of sound and diffraction. If you have not done, then also there is no problem, because I will be explaining diffraction of light from beginning. I mean, I will not assume that you have done many things on diffraction of sound wave. Actually, the phenomenon of diffraction which we are going to do today, it is the strongest proof of wave nature of light. In geometrical optics, light, we assume that travel in a straight line. Actually, it is not so. Light travels in the form of waves only, but our eye is not able to distinguish those ripples. That's why you see it's moving in a, we assume that it is moving in a straight line. Light actually moves in the form of waves with the help of producing wavelets. Wavelets develop, wavelets grow in size, light moves from one point to another point. In diffraction, the light will bend when it is incident on the sharp edge of an obstacle or passes through a very narrow slit. If the slit width is not narrow, you will not see a good diffraction pattern. But if it is narrow, then diffraction pattern will be quite obvious. You will observe that light bends, and if there is a region where there is a scope of interference of two light waves, interference pattern again will be produced. But this time you will be using only one slit, not two slits or many slits. Just one slit will be there. So light, after passing through one slit, according to interference theory in Young's double slit experiment, we have seen that they don't interfere. But here we will observe that a good interference pattern if all the conditions for producing the diffraction pattern is being obeyed in our experiment. I will take the name of two scientists. I will not say that they observed the diffraction phenomenon first. Diffraction phenomenon is natural process. Also you can say that light, after passing through a narrow slit, it bends. Sound wave also, when incident on the sharp edge of an obstacle, it bends, and that is diffraction pattern of sound. Suppose, just let us start with this experiment here. Let me show you one experiment here. Just suppose there is a source of light here. You can assume that source of sound also, no problem, same thing. Just let us take an obstacle in front of source of sound. Okay? Sound also travel in the form of wave. This we have studied, that wavelength, wave velocity, all these things are related. But in this obstacle, in front of this obstacle, if the source is there, then if you are situated here, if the observer is situated here, then the intensity of sound heard by the observer is reduced, but he can hear. The observer can hear some sound if the source of sound here. Why? If sound travels this manner, then it is not supposed to reach here, but it will reach there. This is obstacle. No. Similarly, if you keep a source of light here, if light follows straight line path, then in this region on the other side of the obstacle her observer situated, this portion expected to be dark. This region expected to be dark. This is, we assume that it is source of light. So in this region is expected to be dark. But we observe that light is there. Although intensity is reduced, but we find a portion of light wave in this position also, where it is expected to be completely dark. If light follows straight line path only, then it was not expected. But light will bend here. The wavelet, the wavefront, it sends in forward direction. That wavefront has a portion of it will enter the geometrical shadow portion. A portion of the light wavefront will enter in this geometrical shadow portion. That's why we observe light over there. Region is partially enlightened. And this will observe whenever there is an obstacle. On the sharp edge of an obstacle, it happens. The wavefront incident here, suppose the wavelet situated here, a part of it will be entering there. So some intensity of light always observe. And this part again behaves like a source of new disturbance. So that disturbance again will enter here. This manner, light will enter partially in the geometrical shadow portion. That's why you observe light over there. Okay, it is not completely dark. That umbra, penumbra, all these things, natural phenomena you have studied in junior classes, that is actually bending of light. Not only this, if you send light through a narrow slit, just I am doing one experiment here. Okay, this is a convex lens. In front of this convex lens, a source of light is there. We are taking a source of light here. Then what will happen? Light will pass through it. Okay, source of light. If you keep it at the focus, then light will go this manner. This light also, although I have taken, this light will not, this one will go, because narrow slit we have taken, it will follow straight line path, isn't it? Now if we keep another lens in front of it, then this parallel rays should converge at the focus, isn't it? We are expected to get maximum intensity at this point. Am I clear? We are expected to get maximum intensity where? We are expected to get maximum intensity of light at this point. At this point, maximum intensity expected to be there. If we keep a screen over there, just assume this one is the screen, then you will observe that the intensity of the light, here at this point is like this. And this intensity of light you will observe after this also. After this also. The pattern of light fringe will be like this. So what do you observe there? We have allowed to pass through a narrow slit. Source of light was there at the focus. After passing through this, the light will follow straight line path, passing through the slit. This light supposed to meet at a point. If this one going through the optical center, it will follow the straight line path. All this you know. And a central maximum is expected at this point. At this point, central maximum, I mean maximum intensity, central maximum, what we don't know. But we expect a maximum at this point. What do you observe there? Central maxima is there, I mean maximum is there. But this central maxima is flanked by several maxima and minima, and intensity of light goes on decreasing. This is due to bending of light. Light bends, that's why it is happening. If it doesn't bend, then why you get interference pattern here beyond the central position where light meets and maximum intensity expected over there. But you observe that the central maxima is flanked by several maxima. This phenomenon of bending of light is known as diffraction of light. Okay, so I am just writing one line statement, diffraction of light. You will be practicing everything whatever I am doing here, otherwise you will lose the connection and you will not remember anything after finishing the class with me. So better be ready with your pen and paper and do what I am doing here. Okay? And share it with me if possible. You must make it possible. So you understand? Now I am writing one line statement. The phenomenon of bending of light when it is incident on the sharp edge of an obstacle or passes through a narrow slit is known as diffraction of light. Okay, this phenomenon is known as, phenomenon of bending of light is known as diffraction of light. This diffraction phenomenon is comparable with the size of the slit. Diffraction phenomenon will be more if wavelength of the wave is more. Wavelength of sound wave is more than that of light wave. So in case of sound wave, this bending will be more in compared to the light wave. Okay, that's why even if there is a huge obstacle in front of you, you can hear the sound emitted by the source on the other side of the obstacle. Okay, and actually today's class I will be discussing what is there in your board examination, the topic important for your JEE and NEET examination also, because it is in accordance with the syllabus given in board paper, in CBSE board examination. Okay, so let me discuss that diffraction. In competitive exam, the part they can ask you, I will be discussing with you, but we will not go much details about diffraction. We have limitations here. It is just bending of light, and we will be discussing Fraunhofer's diffraction pattern. Okay, there are two types of diffraction pattern. One is Fresnel's diffraction, the other one is Fraunhofer's diffraction. We will be discussing Fraunhofer diffraction, at a single slit. Okay, So here what is happening, you have understood. So in this diagram, the central maximum is expected at O, but we observe that the central maximum is flanked by several maximum or minimum. And what other phenomenon you observe? Also intensity of light goes on decreasing. Okay, intensity of light also goes on decreasing. Now how bending occurs, let me explain. For the sake of this theoretical experiment, I will be taking the slit bit bigger. Okay, how diffraction pattern is formed over there, that I am going to explain. Taking a lens in front of it, this is the lens and the screen is there, where we expect the pattern, the diffraction pattern which I showed you earlier. Okay, in front of this we keep another lens, focus of this lens there is a source of light. Okay, source of light is taken there. Light, what color you are preferring to select? Let us take that. We will be taking light wave of say this color. It is situated at focus. So light ray becomes parallel after passing through the slit. This is parallel and it is expected to be focused at this point. Okay, maximum intensity will be there and we have expected a bright fringe at that point. Really a bright fringe is formed over there. Now if light passes through the sharp edge of an obstacle, it bends. So this light wave will be bending. This one also bending. And after passing through the lens, they are expected to meet at an arbitrary point P on the screen. This light going and meeting at this point. Clear? We get another maxima over there. Maxima are being formed. This is an arbitrary point where diffraction, light get diffracted and we get this diffraction angle, you take theta. When light get diffracted by an angle theta, we get a maximum over there. It may be a point of minimum also. We don't know, maximum or minimum will be there. And this is the slit. AB is the slit. and diffraction angle, we have taken angle of diffraction is equal to theta. AB, the width of slit, is equal to A. Okay. If we draw a perpendicular here, this perpendicular you can see easily, this is the perpendicular B to M. On this line we have drawn the perpendicular BM. Okay, and this is the slit width. So light in going from B to P or from A to P, the extra path is traveled here. B to P the path length and M to P the path length is looking the same thing. But A to P, light has traveled some extra path length is equal to AM. So AM stands for what? This is extra path length. Extra path length what? The light going from B to P and A to P. This AM, if we have drawn perpendicular from B to the direction of AP, we get this extra length, which is the path difference. So path difference between two interfering waves is equal to, I hope you understand, on AP we have drawn the perpendicular, AM is the path difference. In this diagram, AM is what? If this one is theta, you can see that this angle going to be 90 minus theta and this is going to be theta. Isn't it? From B we have drawn perpendicular, this angle is 90 minus theta, so this is theta. So what do you observe? AM by BM, sorry. Check once. This is 90 degree. 90 degree means AB is the hypotenuse. So AM by AB is required. AM by AB is what? Cos 90 minus theta. Therefore, AM equal to AB sin theta. So AM equal to, AB means what? A. That is A sin theta. Clear? So AM equal to A sin theta. Okay? This thing is A sin theta. Path difference between two interfering waves equal to AM, which is equal to A sin theta. I hope you have understood. Because B to P, this path length, and M to P path length, they are equal. So which part is different? This AM part. So path difference is A sin theta. In Young's double slit experiment, you have seen that path difference is the major factor in calculating interference pattern. In diffraction also you consider interference pattern only. Okay, interference pattern, it is produced by light wave from the point A and from the point B. You can ask me a question, why not a point little bit above A or a point little bit below B? Yes, that is also possible. Let me discuss one by one, step by step. I have considered these two points, these two extreme points to calculate the path difference. But there is no choice that path difference may occur between any 2 points. I'm just maximizing this diagram, you understand. So path difference is AM equal to A sin theta. Now this A sin theta this A sin theta under what condition will help you to get maximum or minimum at the point P, that I am going to discuss. Suppose let A sin theta is equal to 1 wavelength lambda. You assume that, because why this thing sin theta, and that last class we have studied that phase difference equal to what? Phase difference equal to 2 pi by lambda into path difference. You remember, phase difference is 2 pi by lambda into path difference. And we have studied for maxima the intensity, that path difference was integral multiple of lambda or lambda by 2, something like this. Lambda, we have seen that, no? So here we have to see that what happens when the path difference we take equal to lambda or lambda by 2 or 2 lambda or 3 lambda by 2, all these things. Okay? If this is equal to equal to lambda, this explanation is very interesting, because when you are proving something in a subject, then it comes as a natural process, step by step. But for this particular experiment, Fraunhofer, the scientist responsible for diffraction through a single slit, is responsible to make such a consideration that if A sin theta equal to lambda, there will be a minima. He started with this one. The way he explained in his book, we are following the same concept here. But I don't know whether maximum or minimum will be there in the beginning, I cannot tell you. So I am telling let A sin theta equal to lambda. Now this theta angle is very small. For theta be a small angle, what do you observe? Sin theta is approximately equal to theta. Therefore, A theta equal to lambda. So theta equal to what? Lambda by A. This is nothing but 2 into lambda by 2A. Why I am writing this manner? Because I will assume that the slit here going to be divided into two parts. Light from any two corresponding points of two parts will be meeting at the point P to cancel the effect of each other, and we get a minima over there. So then you have to understand this. This is the main understanding part of diffraction. How minima will be formed under this. I have assumed that let A sin theta equal to lambda, and I am going to explain formation of minima over there. Okay? Since theta is small, diffraction angle is not very large. If angle is large, then diffraction phenomenon you will not see. For theta be a small angle, that is when you take sin theta equal to theta, then theta will be lambda by A or 2 into lambda by 2A. In this case, we will assume that the slit is divided into two halves. Okay? Where is the slit? You remember the diagram you all have done? Slit is AB. I am taking a bit bigger than the diagram actually I have taken. And we are assuming that this slit is divided into two halves, AC and CB. And I am going to explain that at the point P on the screen, this time a minima is formed. Why the minima will be there? Because according to him, the scientist, light from any two corresponding point of AC and CB will meet at the point P in opposite phase to produce a minima over there. Okay, so we are continuing that. What we are continuing? This thing, that theta equal to 2 into lambda by 2a. We are working on this. So how will I explain minima over there? A minima is formed at P. In this case, the slit is assumed to be divided into two halves. Two halves, which two halves are there? That is AC and CB. What is happening there? Light from any two corresponding points of AC and CB will meet at P in opposite phase. To cancel the effect of each other. Just one case I have written. So what is happening? Let me explain. What are corresponding points? Point A corresponds with C. A point just below X, a point just below C, they are corresponding points. Okay? A point here just above C or a point just above B, they are corresponding points. A minima is formed over there. This is being explained with the help of wave theory. That we are assuming that it is divided into two halves. Why minima will be there? We have only one slit. So slit need to be divided. Slit behaving like two slits. In interference, in Young's double slit experiment, two slits are provided. Here one slit is there, but it is behaving like two slits. That's why it is written so many lines. Light from any two corresponding points of AC and CB will meet at the point P in opposite phase to cancel the effect of each other. So a minima is formed. Minima is formed at P. So if we assume that phase here is 0, here it is pi, in terms of phase it will be 2 pi. So what is the difference between A and C? Pi. Pi phase difference means they are in opposite phase, they cancel the effect. A distance x below A, a distance x below C, they are also corresponding points. There also phase difference pi exists. That's why when they meet at the point P, they cancel the effect of each other and a minima will be formed over there. Am I clear? So this is very interesting. We have assumed one thing and from there we have proved. But in one case only, this will not be effective. We have to do it for other cases also. Other case means we have to do it when the slit is divided into many number of parts. So let us go step by step, one by one. I said there will be minima when A sin theta equal to lambda. Okay. Now let us show that when it is 2 lambda, then also minima will be there. Now let a sin theta equal to 2 lambda. Theta is small, so theta 2 will be, we take theta 2 here, 4 into lambda by 2a. Previous one, let us take theta 1. What we have taken there? Theta, we take theta 1 because first order minima we got. Are we getting second order minima? Let us explain. We get minima, we get maxima, that only we are explaining. When it is multiple of lambda, then we can prove that minima will be there. Again, in this case also, formation of minima, let me explain. AB is the slit. I have taken a little bit bigger. And this is the point on the screen where light from, in this case you assume that it is divided into 4 parts. No, it has become 3 parts only. We have to make it 4. One, 2, 3, 4. Okay. So how do I write? In this case, here you take 0, here you take pi, 2 pi, 3 pi, 4 pi. Okay. Why I am taking this? Because phase difference pi means they are in opposite phase. So here the parts I am taking like this: C1, C2, C3, and this is B. Okay. So in this case, the slit, AB is the slit. I have taken a bit bigger. I told you, AB is the slit. In this case, the slit is, and P is the point of interference. Any two corresponding point from where? Any two corresponding point of A, C1 and C1, C2. Any two corresponding points of C2, C3 and C3B. Any 2 points. This is true for any 2 points. So in this case, the slit is assumed to be divided into 4 parts. Assumed to be divided into 4 parts. Again, the item will be same. Light from any two corresponding points. This will help you to understand the topic. This will help you to write the answer for descriptive paper. The same manner, the way I am telling you, you need to know, you need to write in your descriptive paper. The slit is assumed to be divided into 4 parts. Light from any two corresponding points of AC1 and C1C2 meet at P in opposite phase. They cancel the effect of each other. That's why minima will be there due to 2 parts. What will happen for other 2 parts? Similarly, it will be continuing. Similarly, about 3rd and 4th part. light from any two corresponding point of third and fourth part will meet at the point P in opposite phase to cancel their effect, and we get a minimum over there. This is the concept. Okay. So what do you observe? Slit first case divided in two halves. Here divided in four halves. Let us draw the conclusion now. Therefore, when the slit is divided into even number of parts, a minima is always formed on the screen. Got it? When divided into even number of parts, this will happen. For minima, what is going to be the condition? For minima, that path reference A sin theta should be in lambda. N belongs to I. Okay? I mean for
that will take for finding the minimum of that even number of
yes. If we take n equal to 1, then 2 into lambda by 2a. If we take n equal to 2, then it will be 4 into lambda by 2a. If we take n equal to 3, it will be 6 into lambda by 2a. In that case, first and second part from their light will meet at the point P in opposite phase, they cancel their effect. From third and fourth part, they meet at the point P in opposite phase, they cancel their effect. Fifth and sixth part, light from any two corresponding points will meet at the point P in opposite phase to cancel their effect. So whenever you divide the slit into even number of parts, a minima always will be formed at the point on the screen. This is the concept. Should remember. Now let us see. So this way it was established by the scientists at that time. Okay? Fraunhofer's explanation I am telling you. He initially assumed that A sin theta equal to n lambda, then explain all the steps. What we are doing, we are studying the same thing but proving it step by step. If n1, see how minima will be formed there. If n2, how minima will be formed. So for minima the condition is A sin theta n lambda. This you can never prove by direct mathematical calculation. Alright, this is for minima. Let us see how maxima will be there. For maxima, I am going to explain. For maxima, what happens? Which one? This is for maxima.
What is
N belongs to I, set of integer. Maybe negative, maybe, I mean, on the screen above center maxima, those maxima minima are there. Below it also they are present. That's why I am taking. You take n equal to W, no problem. Whole number. Okay? But you have to explain that interference pattern is there above center maxima as well as below. That's why I am taking this one as I. For maxima, I am going to explain explanation for maximum. Let A sin theta equal to lambda by 2. You take 3 lambda by 2. Okay? Therefore, sin theta will be 3 lambda by 2a. Theta is small. Sin theta approximately equal to theta 1 dashed. 3 into lambda by 2a. Okay? So here 3 parts we got. What is happening there? Same slit. If If it is divided into three parts, then what will happen? This is A, B, C1, C2 and point P on the screen. Okay? So this I am writing 0 and this is pi, this is 2 pi and this one 3 pi. So it is our explanation for maximum over there. Why maximum will be there for odd? We are doing it, we have started with n equal to 3, not 1. With 1 nothing. Okay? So that's why with 3 you have to start. So there will be maximum or minimum. Minimum explanation already there. Now it is going to be maximum. Why? Light from any two corresponding points of first part and second part, when they meet at the point P, they cancel the effect. But third part, it is uncancelled. Light from the third part will reach at the point P and it is uncancelled. So when it will reach at the point P, although intensity is reduced, because that wavefront you have divided into three parts, one part only reaching, but there will be maximum. So let me write this. In this case, the slit assumed to be divided into three parts. Light from any two corresponding points of AC1 and C1, C2 will meet at P in opposite phase to cancel the effect of each other. Okay? Light from any two corresponding points of first two parts will meet at the point P in opposite phase to cancel the effect of each other. But the third part remaining uncancelled will meet at P to produce a maxima over there. But this maxima cannot have the same intensity as that of central maxima. Central maxima is gorgeous. It is really formed over there, central maxima. It is central maxima now. It is formed over there. Central maxima is there. But this maxima is just like this. Okay? It is formed over there. It is not dark. It is not destructive interference there. Obviously interference, constructive. You get a maxima over there. But this maxima intensity much less than that of central maxima. Why? It is completely natural process. Okay, and that's why I told you in the definition, intensity of light goes on decreasing. Now can you think about a sin theta equal to 5 lambda by 2? What is going to happen? Case 2, if what will happen? If a sin theta equal to 5 lambda by 2, I am not writing, just tell me what will happen.
Is the intensity decreasing because of the distance is increasing?
No, because of a part of the wave front is reaching over there, because the other part is getting cancelled. Okay, this is very interesting. If a sin theta 5 lambda by 2, what is going to happen? How will you write the descriptive part? You will say that in this case we assume that the slit is divided into 5 parts. 5 parts. AB, same slit. We got a maximum over there again. But that maximum intensity much smaller than previous one. Maybe it is formed over there. Maybe you are getting there. But this time intensity is smaller than this also. How do you explain? It is because on the screen, when this complete wavefront reach, light from any two corresponding points of AC1 and C1, C2 will meet at the point P in opposite phase to produce minimum over there. Okay. Similarly, from C2, C3 and C3, C4, when they meet, we have seen that from corresponding points, if they reach, they will cancel the effect of each other. Okay. Fifth part, remaining uncancelled, when meet at the point P, it will produce maximum over there. Is that clear? You understand? Is it okay?
So corresponding points are always in the opposite phase.
No, corresponding point concept remains the same. 5 parts are there, AC1 and C1, C2. From these 2 parts they are reaching to meet at the point P, they cancel the effect. Next 2 parts, they meet at the point P, they cancel the effect. But 5th part, this one is unpaired. When it will reach over there, it will keep some intensity over there. But this intensity much smaller than previous one. Okay, no problem, but we get maximum over there. That's why intensity of light goes on decreasing gradually. Okay. So what will be your conclusion here? Therefore, if the slit is divided, into odd number of parts, a maximum is always formed. So if the slit is divided into odd number of parts, a maxima is always formed. So in general, what is the condition? For maxima, A sin theta will be 2n plus 1 lambda by 2. Understood? This is going to be the n. N again belongs to I. N belongs to I. This condition will help you to understand diffraction when why maximum and minimum will be there. Okay, this is diffraction at a slit, and so far we have discussed it will be Fraunhofer's diffraction. Fresnel diffraction beyond our scope, we cannot study it. Now the question is, in our problem, how to find the width of central maximum. Go back to that experiment where we are struggling with the lenses on two sides. Okay? We will be proving it there. We will be finding the length of central maxima over there. To prove that, what to prove that? To prove that width of central maxima is 2 lambda like this. This central maxima width we are going to find. The lens system I am going to draw here. Lens. Two lenses I showed you here. Light for better understanding, thus width is just little bit is increased. Okay, just little bit. Just a minute. Just draw the light ray. This width, this one we are going to find. So for that we will be finding the position of minima. This minima M1, this one M1 dashed. Linear distance between M1 and M1 dashed is the width of central maxima. That we are going to prove. Isn't it? So in this diagram, do I need to explain? Do I need to remind you? I hope you remember it. Diffraction effect is there, but I did not draw all those things. Because we have proved that for maxima the condition is, although logical proof, but for a board exam this proof only will be there. For maxima A sin theta n lambda, two n plus 1 lambda by 2, this you have done. So width of central maximum is equal to M1 M1 dashed. But M1 how have I got? For minima, first minima, what is the angle? First minima, what is the angle? See, I have to take something now. I am taking this distance is d. Okay, wavelength of light be lambda. And this one, this width already you have taken. This width of the slit is A or D, width of the slit. Width is equal to A. So, what is angular position of M1? That we know. What is angular position of O? That you know, it is 0. So, it is symmetric. You find OM1 and then M1 M1 dashed. This is equal to 2 times OM1. Okay, so for M1 angular position will be enough, then make it double, 2 into OM1. M1's angular position, how to get minima? This is the condition for n equal to 0. For n equal to 0, so sin theta is lambda by 2a. All these things we have done for n equal to 0. And theta is small, so theta is lambda by 2a. So how do you get 2m1 length? 2m1 length, this is very small angle. This distance we have taken d. So OM1 is actually, OM1 equal to actually, the angular position is what? This angular position you know, that is theta 1. Theta 1. So OM1 will be what? Twice OM1 length, sorry, OM1 length. How do you find? That we remember the relation you did in circle. This one say AB. AB is a chord, AB is a arc. Length BS. This one theta, this is R. Then S equal to R theta. Alright, so OM1 will be what? R d into theta. 2 into d into lambda by what? Lambda by 2a. Check once. Oh, for minima a sin theta will be, sorry, it was lambda only, I forgot. We did it lambda, no? For n equal to 1 there. This is for minima, not maxima. This is for minima and this is for maximum, please. So n equal to 1 is sin theta equal to lambda. So theta 1 is lambda by a. It is not 2a. Just we did it. When I was writing, I did the mistake. Theta 1 is d theta 1. Theta 1 is what? Lambda by a. So M1 dashed two lambda d by a. This is formula for central maximum. Central maxima width is 2 lambda big D by small a. I am giving you one simple task. Just show that width of central maxima is twice. Prove that. This is your homework. Prove that the width of central maxima is twice the width of secondary maximum. The width of central maxima, I mean this width of this is twice the width of this. This only you try at home. Hope you have understood the concept of diffraction, what is there in your syllabus. I did not go many detailed about many topic, just what you need to learn for your board and for exam like JEE Main and NEET that I have explained. Thank you.